Good evening and welcome to this program. This is the first of two webinars in support of the program AI for Healthcare at IIT Madras. The next webinar is on Friday the 4th from 6 to 7 p.m. India time. The AI for Healthcare program is meant for students at IIT Madras to encourage innovation and entrepreneurship among them. We have two speakers today and two others on Friday. The webinars themselves are meant for experts in the field of AI in healthcare to share their real-world experiences with the students. And also we have medical experts who will highlight opportunities that exist to apply AI to healthcare to solve healthcare issues and problems. Therefore, we have technology experts and medical experts in each of these sessions. So I think that will be a good fit. Our first speaker today is Dr. ANANT VEMURI. He is currently a senior researcher at the Digital Endoscopy R&D Center for Pentax Medical at Augsburg, Germany. He's a PhD in computer science from the University of Nice in France, and has done his postdoctoral fellowship at the German Cancer Center in Heidelberg in the area of endoscopic visualization. He has over 15 years experience in applying machine learning and computer vision to solving medical questions, especially in the area of surgical technology and surgical data science. So he has a rich experience in collaborating with clinicians over these years, and he has a special interest in the translation of ideas and taking them to the bedside, so to speak. So that's the topic of his presentation today, from bench to bedside. Anant, may I request all others to mute their microphones and to switch off their videos for the duration of the talk. Any questions can be put into a message chat window and will be taken up after the talk.
Thank you very much, Dr. Singh. I really appreciate the opportunity to actually talk about something which I've been working on such a long time, and it's nice to see such an amazing initiative. Can you see my screen? I don't know which screen I'm sharing.
Yes, sir, we can.
You can see the presentation screen because it doesn't kind of highlight which screen I'm.
Okay. Yes, sir, we can see the first.
Okay, thank you. Yeah, so today there are many different topics that I actually worked on in the last few years, but something which happened very recently during my postdoctoral work, I wanted to actually share a little bit about it because it was originally did not start off as my idea, but I just got involved in it, and then it became part of my one of my important works in the recent past. So I wanted to talk about this because it kind of encompasses a lot of aspects of healthcare technology, whether it is AI application, device development, biomedical engineering, anything. So I wanted to talk a little bit about it, and on the way, I'm hoping that I can provide some important takeaways that hopefully people who are on the call can actually be able to relate to and also learn from. Maybe perhaps some mistakes that we made as well. So, so it all basically started. Sorry, yeah, it all basically started when. Yeah. So just a early warning. There is some graphic content because I'm showing you medical video, surgical videos. So I hope nobody gets suddenly queasy in the middle of the presentation. Just a full warning. So it all started when we basically went to the surgical center at the Heidelberg University, which is very close to BIOPHOTONICS and German Cancer Research Center. We kind of spent like a few weeks and months trying to look at what the surgical workflow goes and what are the different challenges that the clinician faces. And then we were specifically focused on one particular surgical technique, which was called colorectal cancer surgery. What basically happens is, if you notice that there is a tumor located in the colon. In order to remove this tumor, the idea is that the segments around that are clamped and blood perfusion stops. You remove, I'm showing a very simplified view of it. So you cut that colon out, you reattach that colon, and hopefully attachment happens perfectly. And this is a critical point we noticed in many procedures, is that there are time and again, it happens that the reperfusion, which is basically the blood flowing back into the colon and all the colon getting reattached, is not happening properly. There's constantly some leakage of blood, and this leads to really complications, really bad complications during the post-operative situation. So we said, okay, this seems to be like a very critical problem, and it is happening quite recurrently. So we said, let's see if we can find a way to solve this. A takeaway that I wanted you to take from the slide is, please visit your clinical partner and observe. It is really, really important, because you get to learn a lot from what they are doing just by looking at what they're doing. If you get a chance, jump at it, and it's really useful. A insider tip, so to speak, when you're visiting a surgical room, or if you're visiting a clinician's practice, take some treats for the hospital support staff. They are your best friends, and if they are not happy, your experience in the clinic is going to be really nasty. So just a pro tip. We went to technology exploration, and then we noticed, what does the eye see? What is the quality of the apple? Where is the whale in, for example, in these images? In standard images from RGB, you can't actually determine this. But if you look at a multispectral image, you can identify hidden structures underneath, and this was something which we thought could be really useful. So just look at this bunch of images. These are actually images of kidney for humans, and which of these has blood perfusion. Basically, perfusion, ischemia means that there is blood supply happening to the organ. It's very difficult to identify just by visualizing it. And I will just show you, if you're able to guess, you have a really good vision. But in typical surgical technique, it's really difficult to identify this. So in order for us to now start off, we said, it was important to have a grand vision of what we wanted to do. I also urge you to have this grand vision while you are understanding your problem, or if you identify a problem, have a grand vision. But most importantly, focus on a specific and clinically relevant problem. This is essential, because you can solve a huge problem, but if it doesn't have any clinical relevance, it is of no use. It cannot be translated. So this is very important. So we looked at the current imaging techniques which are used in surgery. We have a typical RGB camera which takes 3 channels, but if we take a multispectral image, it captures much more deeper details about the details in the surgical view. And what we observed is that a multispectral image, a point at a multispectral image, can easily be used to determine physiological parameters such as oxygenation. How well is the tissue that we are looking at oxygenated? So can we leverage this information in the current problem that we were talking about? So obviously, if I show graphs to the clinician, they would not be happy. So it is important for us to understand what the clinician expects. So our problem from a technical point of view is an inverse problem. We have a image, a multispectral image, a spectral graph, and we want to estimate from these tissue parameters. tissue parameters basically being oxygen or how much blood is flowing through those from the in the tissue, or is it possible to determine tissue malignancy? Things like these are most interesting for a clinician. So an important takeaway I would want to give you at this point is, please partner strategically to develop a good picture, both from a technical standpoint and a clinical standpoint. What exactly are important for a clinician's point of view, and what can you do from a technical standpoint? So that picture needs to be very concretely made before you start working on a problem or while you're working on a problem. So we went and scoured through market, saying, what are the possible hardware solutions we have? And at that time, when we started working on it, we had two very prominent ones, which were, if people who are familiar with multispectral images would already know about this. It's a liquid crystal tunable filter, which have excellent image qualities, and but the integration, the acquisition time for images is super slow. I will just give you an example in the next slide. But another option was a fast filter wheel camera, where it was slightly inflexible, but had a much faster recording time. So think about it. An LCDF camera records at the speed that you're looking at right now. Each image is one wavelength being recorded. While this is happening, I could be, as a clinician, I could be completely doing something else and end up not having the picture that I want. So on the other hand, if we used a fast filter wheel camera, we could choose what information we wanted to record, and then be much faster in our process. At this point, I would like to give away one more takeaway. Please understand your healthcare environment very, very clearly, and unambiguously define what the user needs, because you're not developing something technical for the sake of science alone, but you want to do something that can be translated, so that can make a difference, not just to a clinician, but the end user, who is the patient. Please remember, this is an important takeaway I want you to keep in your mind. So what do we do with this data that we have? So we've chosen this fast filter wheel camera, which can acquire good images, pretty decent images, let's say. What can we do? And the fun starts here, of course. We know from physics, actually we studied a little bit of physics on this because we didn't have background on this topic at that point. We noticed that physics tells us that if we know the tissue properties, I could actually go back and I can model, using the tissue properties, model the oxygenation and blood perfusion in the tissue. But this is a forward problem. I'm interested in the backward problem, especially when I don't have any information about the tissue. And as it turns out, there are some techniques out there which use some like Beer-Lambert's law, which provide a relationship between these spectral measurements that we are taking and the tissue properties themselves. But such kind of problems had issues that we cannot be applied to any camera that we wanted. I mean, we don't know anything about the cameras that we're going to use. We don't know what kind of tissues we're going to encounter, because it's a dynamic field. We can be applying, a surgery could be being done for colon, for kidney, for liver. We need to be able to adapt it. And obviously, we don't have any information of noise characteristics and so on and so forth. So how could we handle this? And after a little bit of after a little bit of search, we said, can we use machine learning to do this? But we need to understand that we don't have any ground truth data to train a machine learning model. So as it turns out, physics-based simulations do exist, where if you know detailed information about the layered tissue of a tissue, for example, if you're looking at colon, if you have a detailed information about this, then you can use Monte Carlo simulations to actually simulate these reflectance values and fit them into the specific camera model that you want. And then on top of it, you can train hundreds of these samples and go and train a model. But before we do anything, it's important that we validate what we are doing. at this point, it is what we did was we took samples, ex vivo samples of, I think we took coffee and pig's blood, deoxygenated, oxygenated, and we did spectral measurements with a device, and we did simulation measurements based on the parameters that we knew, and we checked if they were corresponding or not, and they did, and which gave us the confidence that we can actually use this approach to test what we wanted. An important takeaway I want you to have at this point is always validate your hypothesis with carefully designed experiments. This is absolutely essential because on your way to a translatable product, it is going to be essential that that you have it documented, that this validation experiment is documented. So it's in order to avoid doing it again, please validate and document it. So what we did is then we took this simulated simulations from the tissue properties. We trained a simple regressor. In this case, we trained a random forest regressor, and then applied it to the application that we wanted. And as you can see, we were able to measure the blood oxygen saturation, because this is done before the clamping was applied. And you can see that we can already estimate the blood fraction. Enjoy your moments of success, because there are always going to be difficulties on the way. So when you actually accomplish something, please make sure that you take some time to enjoy that moment, because then actually, as it turns out, we wanted to apply to other tissues. I mean, for example, we wanted to apply it to be more generalized for a kidney procedure or something. And then we spent 6 to 8 months scouring through literature from biology to biochemistry to a lot of things, and to look basically for very specific tissue properties which we could use without to train our model. And we realized we need to get in, because we did not find any tissue parameters which were reliable enough. And fortunately, because we were in DKFZ and the German Cancer Research Center, we could speak to some biologists there, and they said it's an extremely difficult task that you're asking, and it is probably not possible for us to do it under under the conditions that we have right now in our lab. So this kind of got us a little bit disheartened. But remember, please don't give up. These kind of problems will come. You will be able to find a solution if you just have persistence. What we did was one of our team members actually got an idea. Why not take the parameters that we already have for the colon? Let's just make the range of these values large, and let's just generalize the tissue that we want to simulate. And we actually did that, and we trained 500,000 samples. And it's not just enough to train the samples. We need to make sure that we actually have some meaningful values there, right? So it's a wild hypothesis we had. So we wanted to first test it. In order to test it, we actually projected our data set into basically on a 2D surface, and then projected. So we made measurements, spectral measurements, using a spectrometer basically on a dead and an alive pig on one of the tissues, and we found that actually these values started making sense. But it was not enough to do it on one pig. So we went on and did it on 5 different pigs and 5 different tissues. And we found that on almost all of them, the values were matching with what we had predicted, what we had simulated rather, excepting in one case, which is gallbladder, and which was actually a really good checkpoint for us, because here we realized there are some chemicals which are there in gallbladder which have special properties for which we didn't account for in our simulation, and so they were not fitting into our simulation, and that was sort of a pseudo validation check for us. So having armed with this fact, so I want to go back again to this takeaway. Again and again, I'm going to tell you, please validate and document your validation experiments very carefully, because it's going to be essential at a later point. We armed with this, this huge data set. We trained a simple regressor, but we needed to adapt it to the domain. We could easily adapt it to the domain that we wanted to apply it in by just taking unlabeled data and just making sure that this data kind of was weighted in a way which fit. So we could fit our training simulated data close to this unlabeled data, and we could now train a regressor and apply it in a clinical scenario. So before I go to show you what the clinical scenario could be, now I come back to again that laparoscope design. The reason I'm talking about this again here is this is a really nice camera. It gives me like probably a slightly higher than high definition image, but it's about 4.5 kilograms. And I don't know if anyone has actually been to a surgical room, but a laparoscope typically maybe half a kilo, not more than that. And it's a really tiny ergonomic thing. I'm going to show you a picture of it later. But this device, as it turns out, it's super heavy for a clinician. And the frame rate that we could capture from it, at best case, after super optimization, was 15 FPS. If you see any surgical room, typically the cameras are showing you images at 60 FPS. 15 and 60 FPS, the clinician is going to tell you, I'm sorry, I don't think I'm very comfortable looking at the images from this. So we had to go back and check. At this point, I want to give you another takeaway. Please understand your healthcare environment that you're working in, the domain that you're working in very, very clearly, and unambiguously focus on the user need, because it's for this user that you're developing this technology. So please focus on this very, very closely. So as I said, you can see the laparoscopic camera. It is this size, and I showed you the camera that we had earlier. It just fits into the palm of your hand very nicely. So we spent close to 3 to 4 months meeting with industrial companies, basically different companies, approaching different research centers, trying to identify if we could find a multispectral camera which was tiny enough. After about 3 months of search, we came across IMEC, which is a Belgian company. We visited their offices in Belgium, and we did extensive testing. And we found a device. They were the first manufacturers of a snapshot multispectral sensor. And what was amazing is that it was really tiny. It could just feel like a laparoscopic camera in our hands. And we did extensive testing for a couple of months to make sure that it fit the requirements that we had. And then we said, okay, this is the device which we want to use. And I'm not going to go into details of what we did after that. But what I want to show you is finally like a little bit of application of this device in a clinical scenario. So we went back and we were, if you remember, one of the pictures I showed you was of a kidney procedure where the surgeon was basically cutting out tumor from the tissue. But before we cut out the tumor from the tissue, it's actually important to stop blood flow to the tissue. And typically this is done using a very complex procedure, which is not repeatable. So if you're wrong, you have tough luck. You need to still go ahead and do the procedure, even though you're not sure as a clinician that the clamping was successful or not. So we said, okay, can we use our camera? And as it turns out, you can see here, a clamp is being applied, and you can see that the oxygenation in the tissue is going down. And we could see this in live at 35 frames per second, not the 60 frames we were expected, but it was well enough for our clinician. And once the surgery was done, they opened up the clamp, and we could immediately see the blood reperfusing the tissue. As I said, we had a small vision. We wanted to apply it on different scenarios. Now comes the grand vision. Can we apply it to more applications? We actually went to a clinician in Department of Neurosurgery because this guy wanted to see how well can we visualize spreading depolarizations especially in a stroke patient. And as it turns out, we can. I don't know if you're able to see it clearly. You can see a wave of these. This is basically oxygenation map on the here, and you can see waves flowing. There is an artificially induced stroke in the brain, and these waves propagate along the surface of the brain, causing damage. To study these helps the clinicians to determine what kind of medication can be given and how quickly do we need to do this. And this was really useful because this led to more studies in the future. This work was not possible just by myself. We had a lot of people working on this topic, not just from university point of view, but we had clinical collaborators and we had industrial partners as well, which we were not officially partnered with. So I want you to have a takeaway here. Please remember to forge partnerships. You can't do everything alone by yourself. It's important that you have good help where it is necessary. So learn in the process where you can forge partnerships and build them. Some key lessons, apart from what I've already mentioned, is please always keep the user in mind. The user is the clinician, of course, but the user is also your patient, because it's what we are going to develop is going to make a difference to the patient. So keep this person in mind and make sure that any software, any device that you're building actually works and improves their quality of life. As I mentioned earlier, make sure you forge partnerships. You cannot work on everything on your own. Key partnerships will help you to make this project more successful. Also, throughout the project, if your goal is to translate a particular idea or concept, please always keep doing an assessment of what is the impact on health of your product, of what you're going to develop. Because this is it's very easy to lose sight of this, but it's essential, because what you design, it will essentially be reliant on this assessment that you make. And finally, I want you to take away that innovation is not a linear process. You can draw it in whichever way you want. One of the ways you can visualize it is like a circuit. It's a circular process, but the center of it is an integration hub, which basically manages the information flow across different aspects of the project. Be the integration hub for your projects. That will enable you to be able to control the translatability of your product and also the success of your product. So with that, I would like to thank you for your attention and open up for any questions, any discussion points. Thank you.
Thank you, Anant. You're awaiting any questions? Meanwhile, I have one question. How different is it for a student researcher to work in this field compared to a researcher in industry? In the collaboration framework, what collaboration framework do they typically work in with clinicians, as opposed to someone in industry working with the clinician, especially with students and researchers have a time-bound certain period of time in which to do some initial work. So what would you advise in this matter?
So yeah, actually, it's interesting because I moved from academic research to industrial research, and I see it. So when as an industrial researcher, if I approach a clinician, they always look from a commercial standpoint, and the same thing when I approached, I could freely approach a a researcher, a clinician, as an academic researcher on any topic. Basically, it could be a wacky idea to just a concept, and it was possible for me to approach the clinician. So the difference being that as so in industry, if you're working in an industry, there are bounds that you always want to work within the framework of. First of all, identify if this idea is something which is feasible to be translatable. But when you're working as an academic researcher, you have the choice to work on something a little bit novel, which you don't have an idea whether it is translatable or not, but you have a vision of a scientific idea being helpful in the clinic. And so there is this gap associated with it. If you're working at, so if you have a short time-bound project, for example, if you're working as a master's student or and you're looking for a project, you have very short time, focus on a specific, you have a grand idea, it's good, go to the clinician, discuss with them, spend time in the clinic to understand this problem, understand their environment, and see if the concept that you're talking about fits in, and then discuss with them at a very detailed, because clinicians are not very good at imagining things that they haven't seen before. You need to explain with drawings, with conceptual, simple concepts. If you go approach them with such stuff, and if they are inclined to investigate, they will definitely and then you can focus on a very specific aspect of the project. So from a time-bound aspect, I would say do this. If you're working as an industry, you don't have to, because you'll already be talking about time-bound. Can my product be? Can the idea be translatable? You're already starting from the very first discussion. Is this a translatable idea? But as an academic, yeah.
Thanks, Anant.
Yeah.
So there is a question. You want to ask that and then I'll ask?
Sir, I think I'll ask from the chat then. Your voice is echoing. So the question is from Krishna. How does one quantize or measure the impact on health of your product software to be a part of the development cycle?
So in general, there are, so impact on health is typically identified. There are no specific measures to do this. But what is important is when you have, if it's possible for you to have, we talk about what is called as KOLs or key opinion leaders in the clinical field. So if you have an opportunity to talk to clinicians, KOLs are basically people who are experts in this area, in the clinical area that you are targeting, and they will be able to provide you some feedback on what your idea or concept can be will have an impact on. So what I would do is, if you have an idea, if you're able to sufficiently detailedly explain to a clinician who is able to understand it, then I would say explain this concept to at least 3 to 4 clinicians and prepare a very detailed questionnaire, which allows you to assess what they feel about this particular product. It has to be a very detailed questionnaire because, this is something which you will learn as you practice, and this is whether it's in a development cycle when you're doing a product, software development, or you're building a device. At each time, this helps you to provides let's say, detailed feedback on how the idea that you have is going to be reflected in the clinic. I hope that answers your question, Krishna.
Yeah, Krishna says thanks, and we have another question, sir, from Lakshmi Narayan. In general, we are facing issues in accessing healthcare data. Without data, we can't make models. How to approach and deal with this problem?
This is a perpetual problem. We can't, unfortunately, there is no easy way to solve this. What is good is that, like right now, for example, you are in IIT Madras, and there is a research center which helps you in development of your development cycle, so to speak. And it also provides you infrastructure for storing data. So what I would say is, when you are forging these partnerships should not be just between individual level, let's say from you as a project owner with a clinician, but rather it has to be more institutional. So forging into institutional partnerships helps to come to an agreement and of creating data repositories for at different institutes. And this is what we have done. Actually, in Human Cancer Research Center, when I started out, when I joined or when I started, we had a grant from the German government, which allowed us to build a separate center, which would act as a common connection point between clinical as well as engineering parties. So, and it acted as a repository. A lot of issues come here because it's not a small field. You need to consider data privacy, data security, and all these things. It's not an easy thing to, but at an institutional level, if this is something which needs to be tackled typically. Otherwise, for small projects, I would recommend going into scouring through research papers, because there are in communities like in MICAI. MICAI is an organization which does a lot of. I mean, it's a conference as well, but it's an organization which does a lot of data validation and things like that. So there are a lot of competitions, and you can find in these competitions openly available data, which you can reach out to the organizers of these competitions and download them. It depends on the kind of data that you want, of course.
So, Anant, this is Arun here.
Hi.
Thank you for the talk. I cannot agree any more with you being a researcher working in imaging field, with the advice and the comment on how to forge alliance and with the clinical partners and stuff. But I would like to wear the hat of a student, right? Apart from that, could you share the insight about how the teamwork from different disciplines, right? You said you computer science, so we have electrical, mechanical. That's how we are all pocketed. So from the student team or from the engineering team, within the engineering team, leave alone the institutional alliance with the clinical partner, within the institution, within the student teams, how important or how necessary is this interdisciplinary collaboration? What's your comment on that?
So to understand your question more clearly, Dr. Vijay, so are you talking about the interdisciplinary nature of how all the different fields you mean? Like mechanical, electrical, computer science, and so on?
Have collaboration between students from different backgrounds, like computer science, electrical, biotechnology. So from your experience, both from academics and to industry, I'm sure you will have an insight on that part.
It's actually interesting, because when we were working on this this project that I presented to you, we initially collaborated with clinicians from 3 different hospitals, industry, 3 different hospitals, but 3 different departments: neurosurgery, general surgery, and urology. And in each case, we needed to spend time, spend time in their respective centers to understand what they were doing. And on top of it, there are physicists involved. There are electrical engineers. So we did not necessarily watch. We were really fortunate because we discovered a company which built this device, this multi-spectral imaging sensor, which was already there. But if you're working on projects which are a lot more core, let's say basic stuff, where you're building something from scratch, it is, as a software engineer, you can only do as much if your device is not able to meet your requirements. So you need a collaboration with electrical engineers, with devices, someone who is expert in sensor technology, for example, to be able to do something. Additionally, when you are putting this device together, don't underestimate the need for the importance of ergonomics, or the design itself, because what we hold as an engineer on our table and what we take into the clinic has to be, there's a big gap between the two. It needs to be bridged, and the design engineers or mechanical engineers are super essential, because it's in our team in Pentax, in digital endoscopy, and also we have a small team, about 35 people. We have 5 to 6 engineers who are kind of experts in different scientific fields. But we have 10 mechanical engineers. We have 5 electrical engineers. We have a separate software team as well, who are dedicatedly working only on software so we as scientists, we only work on the concept, the proof of concept, but we need to engage all the other teams to be able to get our product finally into a prototype phase, which can be taken even for a simple benchtop study or an animal study, for that matter. So it is these. I can't give in a very short time an example, but it is very essential that people collaborate, especially when building devices, and even for that matter, software, because what you build, what you work on your computer on your table is very different from what goes on the side of a patient, for example.